which
Professor,
yes.
Your camera isn't on.
Are you sure?
Yes.
My camera is not on, but can the other also confirm this?
It's okay. It's open.
Huh?
Okay for me now.
It's from you. Okay. Too.
It's okay? Okay, so can you double check? Because I believe...
Okay, let me rejoin.
Are we good now? I believe the camera is on, but you can also remind me if something is wrong. Okay, so as we were saying, we can, after we learned about linear transformations, the topic that we tried to cover, it was a change of basis. And we assumed that if we are in a certain domain, which is composed of a specific basis, this basis could be B1, B2, and B3. We learned that we can go from one basis to another, and we often use the standard basis as a bridge. Okay, so if this was a standard basis, one could go using a matrix P1, and you could also go backwards using P1 inverse, and again you could use P2. You go backwards using the P2 inverse, and similarly we go here with P3, and we go back with P3 inverse. Now, this is the fundamental knowledge or relationship from one basis to another. Okay, we can use the standard basis, which is composed of vectors, which we denote them as E1, E2, and En. Okay, so if the space is three-dimensional space, then we are talking about 1, 0, 0, 0, 1, 0, and 0, 0, 1. So this would be the standard basis for R cubed. The standard basis for R4, it would be slightly different. So we can have a four-dimensional space. A good example of the four-dimensional space could be the space-time, which is the merging of x, y, z, end of time. Okay, that is legal. You can do it. You can say it. But I need to adjust something here, which here we would have another one. So, and now this is something that you can remember. Okay, that you should remember. And often, even if you do not remember the tricks or the matrix which ensures to pass from one basis to another, and when we're talking about from one basis to another, the types of transformations, they are going to look like this. So we can have a vector, which is vector x, which is a point in space. It is fixed, but it is projected differently on different bases. This would be B3. So a vector x, according to the, if these are the values which are projected on the basis of B3, and we want to represent this one, how this vector is projected, let's say, on B1. How we do it, anyone who can help me here? You can raise your hand in the comment section.
First project it on the standard basis.
Yes, who is talking?
Sorry?
Yone, okay.
Oh.
So how do we project this one on the standard basis?
First we project it on the we multiply it with P3.
We apply, you said multiply, which is okay.
Okay, apply.
We apply this linear transformation because multiplying by a matrix, you are very correct, they are equivalent. Yes, and then?
And then we project it on standard basis. Then
yes, now we are here.
We are on standard basis. If we want to project it on the basis 1, we apply the linear transformation P1 inverse.
That's correct. Okay. So this is P1 inverse, and this would be equal as the vector x as on B1. Okay, that's it. Now, even if you don't remember, sorry, we need an equal sign here. So even if you don't remember this, you can, if you don't remember the theory, because the theory is a little more, it has more fundamental principles, which also report that the transition matrix M it is equal to, even the last time we derived the transition matrix M, which in principle, you can easily see that the transition matrix is this one, okay? Because this can be written as transition M from basis B3 to B1 times X, okay, fine. Now, there is one little extra trick, which you can see it in the textbook. You can read it, it is important to understand. But even if you don't understand it, you can always go back to this piece of knowledge, that's enough, okay? But a more detailed, a more intimate relationship of how the transformation matrices can be related to each other, these can be, this is defined as what we wrote from the last time. So any vector V, we try to transform to see how these are projected on B, wait a second, on the new basis B prime, or V2 according to B prime, and so on. If you look at the examples of the last week, you can see them there. Now, this was the change of basis. Today, we're just going to look at a couple of examples of how we change the basis, and then we're going to talk about the diagonalization. We said the last time, there are some tricky things which I want you to take them with you after you graduate, even after you graduate, including also after you take the linear algebra course, which is that we do linear algebra only for the diagonalization. That's it, okay? That is the most important aspect that in linear algebra that you are going to find it very useful. So after a couple of examples, we're going to start about diagonalization, which includes knowledge about eigenvalues and eigenvectors. Now, let's see, let's have an example. So this is the major, the fundamental essence that we care about the change of basis. But I like to have the examples written all in one piece. I hope this is clear. Let me take this out. And I can leave this, and this is gone. So, with this example, I believe you can see this part. So, assume that we have a basis B, which is composed of vectors 1, 2, and -1, 1. And we have another basis S, which is composed of 3, 1, and 5, 2. So here we have the two bases, and the question is, given X according to basis B, which is equal to 4 minus 1, and we need to denote this also, given this, and okay, so you can separate this one. So given this vector X, which is projected onto B, find X according to basis S. So this is what we are saying. Now, simply what we would need, so if we preserve the terminology here, this is B and S, so let this be B, let this be S, apparently, we just need to multiply, so we have the data in B, we go to the standard basis employing this matrix here. So if we follow this formula here, we have the basis in B, okay, and we first go to the standard basis, which we go with a matrix B, right, and we move into basis in the other basis, which is matrix inverse S, okay. So this would be the solution in matrix S. That's it, okay? So this much, I expect all of you there's nothing to memorize. It's more beautiful than difficult, okay? It's not difficult at all, but it is very, very beautiful. Let's move on. So here, let's do this step by step. So in principle, or we can do it just fast without wasting too much time, which is here, what is XB? It's 4 minus 1. What is the matrix PB? It's composed of the basis vector B, which is 1, 2, 1, 2, minus 1, 1. And then we have to multiply with the inverse of this matrix. What is this matrix here for, or let me call it this way. Matrix PS, which is a matrix which is used for the basis S, this is equal to 3, 1, 5, 2. Now, the inverse, I'm not very good at memorizing, but it looks to me, first of all, what is the determinant? Determinant of PS is equal to
1.
Thanks, this is equal to 1. And the inverse here, it looks like it's going to be integer numbers because we know that the inverse is 1 over the determinant times a few other terms. So once we see this determinant equal to 1, I want all of my students that take my course that they should immediately notice that this is a unimodular matrix. Okay. So don't forget this. They are very useful. You should also intuitively and always remind, okay, that's a good matrix, it's a unimodular one because the determinant is equal to 1. It might preserve, it does preserve several properties. What is the inverse? The inverse I forget, but is it something like, who remembers this? Is it 2, 3, they change places here?
Yes, and minus 5, minus 1.
Okay, I hope this is correct, but if you confirm it, this should be correct. Then, okay, so here we have, what was this? 2, 3, minus 5, minus 1. Okay, so then let's multiply here with the PS inverse, which would be 2, 3, minus 5, minus 1. And let's find this step by step. So let's multiply these two here, which is we multiply this row with this column, and what do we get? That row times that column, it's 4 plus 1, this is equal to 5. And then we have 2, 1 multiplied by 4, 1, so we get here 8 minus 1, 7. Is it correct? This looks like right. And then we multiply this with a vector 2 minus 5, minus 5, 3. Here, we just get, and by the way, what is 5, 7?
It's in the standard basis.
Perfect. Okay, so this is in the standard basis, which means that, I mean, or let's do it all, and let's do it step by step here, so that we just understand that we really need 2 minutes to solve such a problem, not anymore. So here we have 2 times 5, it's 10. 10 minus 35, minus 25. This is minus 25. And then we have minus 5 plus 21. This makes it 16. This is 16. Okay. So we multiply this, and this is according to basis S. What this was basis B. So we can see everything on the board. We have this projection on basis B. This is the vector in standard basis. This is the vector in the S basis. Okay. So if we are to draw this one here, I always like to show it in this way because it is really helpful. So apparently we had a vector here which was 4 minus 1. This vector in the standard basis, it is projected on the as 5, 7, and in the other basis, this is minus 25, and this is 16. This is S, this is standard basis, this is B. Okay, so this is all. Okay, I mean, I just want you to pick up this very soon and not wasting any time. Okay, then. So this is the change of basis, and the change of basis and similarity. Now we are going to talk about the property which is called similarity between the linear transformations, and two matrices are called. So we are going to talk. So this was a good example. Any question for what we have so far? So this was the initial question. We are done. But as a small reminder, we can say that x, in principle, in the standard basis, it will always be equal to 4 times, because this 4 is a projection on the first vector, which is 1, 2, minus 1, which is a projection onto the second vector, which is minus 1, 1. And this is equal to 4 plus 1. And here we have 8 minus 1, 8 minus 1. And this is equal to 5, 7. Okay? So this is what we got. But it is good to have a look at these, assuming, looking at carefully, that this is the projection on these. Now, let's write the standard basis. Similarly, it looks like we find the answer, which is minus 25, 16. Now, the same value of x, the same value of x in the standard basis would be equal to minus 25 times what? Times the first column, which is 3, 1, plus 16
Times 5, 2.
5, 2, correct. Thank you for confirming this, 5, 2. Okay, so, and then, this is how it is. We cannot say much more about this. Now we move to a new topic, not a new principle, which is called similarity. So now we're going to talk about the similarity, and here the concept of similarity is the following. If we have any matrix C, which is equal to, which can be written as P inverse A times P, so if this is possible, all of these are matrices, then we say that C is similar to A. Okay, this is what we're going to say. But now, that's all. And this similarity and these not these properties, but these types of relationships, we're going to see this very soon when we do the eigenvalue equations and when we find that a matrix can be diagonalized or not. But it's not, this is all that we need, but in principle, we can also define this one as a relationship between the transformation between different bases. And wait a second. Give me one second. So let's say that now the principles that I want to write on the board, they are very much similar to what we have seen so far. So I'll try to summarize them. I just want I want to remind you that vector x it can be written as a PB times x in basis B. Okay, it's the vector x projected in the basis B, and this is the matrix which is composed of the columns of the basis B, and this is the x in standard basis. Okay, this one we do remember, but now we will say that any linear transformation T, because we are still discussing the linear transformations, the LTs, this can be written as a matrix A times this vector x. Okay, and now if we substitute here instead of the vector x, let's substitute this expression. Okay, so we get this from here. We substitute here. What can we write? I hope the blue color is off. You can see it from there. This would be equal to the matrix A, which conducts a specific linear transformation, times this expression, times PB, right? As a reminder, this is also a matrix, times the x in the basis B. And then we can define a linear transformation, which is T of x, the same linear transformation, but in another basis, which can be B prime, and this would be equal to, so we know that this linear transformation, which in principle, what is this? What can you say about this one? Or let me ask you this, what is the dimension of T of x? This number here. Yoni, since you talked about, I think it was you that you were speaking. What is the dimension of this linear transformation T of x?
The same with the other. I don't know.
Well, think about this one. Let's have a look at these terms here. What can A be? A can be 4 by 4. Okay, fine. What can be P? P assumes another 4 by 4. It's okay. What is X? X can be 4 by 1. It is a vector. Okay, let's assume this much. Oh, sorry, this is 4 by 1. So this is 4 by 4. You have a matrix P, which is 4 by 4, times X, which is 4 by 1. That's good. What do you get as a result?
4 by 1.
Perfect, 4 by 1. So it looks like this one here is just a vector, okay?
Yes.
So this T of x here is a vector, don't forget it. You can even write it down, we can write it down to remind ourselves that we're talking about a vector, because sometimes things might look complex, but they are not. I'm looking for the eraser, sorry. So apparently it's just a vector, and but our intention will become clear right now. So we want to represent this linear transformation on x, which is going to be another vector, which is also a vector n by 1. But the projection in basis B1, it can be written as P B prime inverse times T of x, okay? And this T of x is in the standard basis, okay? But this vector in standard basis, we know how we can write vectors in standard basis, right? This is how we can see them here. So then we get this, and this is equal to P B prime inverse times the matrix A times the matrix PB times the projection in basis B. Okay, so the reason that we are writing all of this is the following. So we know that always, so I just want to remind it, but let me write them here. So we know that any linear transformation is applied on some vectors, and this can be written as AX, right? We have to find the matrix A, which represents the linear transformation. And how do we do that? Do you remember how we find it? We used to do it like this. So what is A? This is equal to the linear transformation on E1, right? Linear transformation T, which is this on E2, on this standard basis. Linear transformation on En, this is just a reminder, right? And we multiply with the x, that's fine. That's good. But now, what we want to do is that this linear transformation is in the standard basis. Now we assume that, actually it might look like confusing, but we are kind of repeating the same thing again and again, because they are important. So now we have the same linear transformation here, but we want to see how does this linear transformation look in basis B, and how does this linear transformation look in a basis B prime. So in principle, we are trying to write down the linear transformation in basis B prime, which is this one here, as a function of the linear transformation in B. Okay, so far we did how the vectors transform. So how did the vectors transform from one to another? So here we call this one. This was the PB, right? This will be or that we call PB. This will be PB prime, because we are using a new notation. Consider this B prime. So we always go on like this, and apparently we have a vector xb here. We multiply with PB, we multiply with the matrix, which is here in this domain, and then we move away this way. Now we have two things. Now this schematics, this is the most important schematics that you have to remember from this course. You can always go back to the recordings and just look for these schemas, because they will help you a lot. So far, we have done just the linear transformation of vectors, okay? Which means the following. We have a point in space, and this is how we look at it from different bases. But what is the most essential part that we need to do, and which we are going to do, and these schemas that you see here, we're going to see some new component. The new component that you're going to see here is the matrix A. Okay, so so far we don't only need to transfer to see how the different matrices, the different vectors look in different bases. We are also very much interested into figuring out a specific A, which is in the standard basis. How does this look like in, let me call this one matrix A according to basis B? Okay, sorry, this is B. So we care about this one. Also, how does matrix A look according to B prime? This is B prime, okay? So, and in fact, we know that if we want to see how a matrix looks like in different bases, what we are in essence trying to represent is how do this linear transformation look in different bases, okay? They are all equivalent. I just want to, forgetting all the words I've been saying, try to eloquently report what the essence is. You can always remember this, okay? This schema. Standard basis, B prime, different bases. We have vectors which can be projected differently. We agree with this. We solved many examples, so we know it very well. You know how to derive these. But we have a next step, which is very important, which is this, that the matrices in standard basis, they can be the linear transformation represented by this matrix has a configuration in B, has a different configuration in B prime, and being able, and in principle, let me say also this one, these matrices AB and AB prime, they will be called similar if they can be represented by an expression which you see here on the top of the board, right? So this is the similarity representation. Now, allow me, so this is the summary of what I could have expressed mathematically in slightly longer details, but probably we don't need that much. Okay. Now, I believe there is a theorem. We can write down a theorem regarding this. It's good to look at the problems in a formalized way. And this theorem records the following. Let me say also that this similarity relationship, we are going to consider this one only for square matrices, okay? Or let me write it like this. A is equal to n by n, which means that this is a square. So keeping in mind that this is square, we're going to get this. Now, let's report this theorem, which is simply, we often report linear transformations that go from Rn to Rn. And this T is a linear transformation, and B is a basis of Rn. B is equal to x1, x2, xn. Okay, here's a basis. B is a basis, and we have also, we have a Tx is equal to Ax. We have seen this a lot. We know how they look like, and now, so if this is the basis, in fact, we have also that the transition matrix P is equal to what? The transition matrix P is equal to x1, x2, xn, and there is no much new information here. So let me write this. This is the, so this B is the basis, and this is the transition matrix. Okay, this much we know very well, and then we can say the following. The linear transformation T on X according to the basis B, okay, this is equal to P inverse A P X B. Okay. Now, the theorem, it is clear, but simply we can write it in this way. We can say the following. A represents T in standard basis. Okay, then P inverse A P represents this T in basis B. Okay. Now it's not a lot of information. It's just that you can either read this. Sorry. Okay. This one in blue, or you can read this. They are both equivalent. So if you think this might become a little confusing, but it's not actually. You can only remember this. If A represents a linear transformation in standard basis, P inverse AP represents linear transformation in the new basis B. Okay, that's it. And now, if we consider, I don't want to make. Let me add another statement, which is the final statement is that C is this P inverse A times P. Now, I don't want to write this here, but this one is called the matrix C, and in this case, this is what we wrote at the beginning, and C is similar to matrix A. Now, this is all that we can say regarding the similarity relationships. Okay, is it clear? And one final thing that I want to add, which I want to use this one for the future example that I'm solving on the board, is the following. Now, this is such a beautiful thing. I don't want to erase this, but let me take this. So this theorem is represented down here. I'm going to leave it there for a little longer. This will go, and this was also. Now, I want to ask you, how do you describe the equation of a circle? Arete. Сега го вземем арете.
X катрор плюс Y катрор values на R катрор.
Yes, and this R squared, this can be something like this: x squared plus y squared is equal to 1, right? The radius can be 1. And similarly, you might have seen also cosine squared plus sine squared is equal to whatever we have there. But let me ask you also about this relationship. What is this equation? If you have x squared plus 4y squared, this is equal to 4. What is this? So this graph here, x squared plus y squared, this is equal to 1. Okay, this is 1, 1, minus 1, minus 1. You agree, right? What about here? What is this equation here? Let's do it like this. If we assume just epsilon is 0, such x.
هذا minus 2.
في equation درس ellipse graphical.
That's true. This is an ellipse, so this is a circle. You found it. This is an ellipse. So if we set y 0, we get 2 minus 2. If we set x 0, choose x is 0. What is y?
1 and minus 1.
That is correct. 1 minus 1. So then this is a continuous function. We see an ellipse. Okay, that's good. Now, keeping this in mind, let's look at another example. But probably let's take this also away. Okay. So let's assume that we have an equation which is 5x squared plus 5y squared minus 6xy. This is equal to 2. Now, in 2 minutes, we will learn how to express this identity, which is a function of two variables. If we have two variables, x and y, can we represent this as a vector? We can, right? So what I want you to see here, I want you to try to observe how it is possible to write this one as a relationship as a function of vectors. And now, what we want to do is to do the following. X transpose times a matrix A times X, this is equal to 2. Okay? So I want you to notice this, how we can write this. Let X be. Now, I can show you this step by step, but I want to write down the answer because I'm sure you're going to understand it right away. Let this vector X be equal to X and Y, okay? This X and Y that we observe here, that's what this vector is. And then I want you to see this X and Y, because this is the vector X, this is transpose, right? It becomes a row. It is a column, so this is 1 by 2, this is 2 by 1, then we multiply this by a matrix A, which is equal to 5 minus 3. 5 minus 3 minus 3, 5. This is 2 by 2. And then we multiply this with the xy, which is 2 by 1. Now, what is the answer here? What do we get if we multiply vector, matrix, vector? What do we get here?
One by one a matrix.
That's true. 1 by 1, it's a scalar, right? A matrix which is 1 by 1, it is a scalar. What is a scalar? Subject to numeric. Well, in this case, it's 2, right? Let's not forget. I'm trying to write this here. And why do we have that equation down here? Because if we multiply, what is the result of this multiplication? We should get a vector which is 2 by 1, right? Because this is what we get. We have 5x minus 3y, 5x minus 3y, and here we have, wait a second, what is this? Is it true? Is this correct?
Plus 3.
Okay, plus 5y, this is a vector 2 by 1. And then if we multiply this with xy, this will be equal to, we multiply the first row, it's a single row actually, with this, with these two. And this is 1 by 2, 2 by 1 times 1, sorry, 1 by 2 multiply this. Let's see what we get. We get x times 5x minus 3y. This is
5x squared.
Yes. Okay.
It's the equation.
Yes, it should be. Okay, we see this minus 3xy is minus 6xy, okay? But I want you to remember this. Okay? Even if you have 3 variables, you can do it, which means that if you have x, y, z, and you have a polynomial of 3rd order or 2nd order with 3 variables equal to a scalar, now you have all the background how to be able to write this one, okay? So, try to remember this. And now let's look at the problem. So let's we have 2 variables here, and we have let's assume we have a point. When I say a point, what is a point? A point can be this point P, right? This point P can be represented by a vector, right? And this point can be x and y, simply. This x and y is a point somewhere in this basis, and the projections we have to figure out what they are. So let's assume that we have, let me write it like this, we have xy in the standard basis. I could simply write it, but let's remind you that it's a standard basis. And let this same point, let this be equivalent to another, we denote this as capital Y, capital X and capital Y in the new basis B. Okay, then what we can try to do is assume that we want to rotate the standard basis by pi over 4. So let's do this. Rotate standard basis by pi over 4. Now, how can we rotate the standard basis by pi over 4? This is pi over 2. So how can we rotate it by pi over 4? We know that we have a matrix which is cosine pi over 4, right? We've done this before in the last week. This is minus sine pi over 4. We have here sine pi over 4 and cosine pi over 4. This is the rotational matrix, and the state here long enough, we can take this away. And okay, and this matrix here, then it's going to be equal to, so this is equal, this is 1 over square root of 2 times 1 minus 1, 1 minus 1, 1, 1. Okay, we know this much, and then we know that any vector v in the standard basis, it's always equal to the matrix P, okay, which will in fact be this, because this is the rotational matrix. So let me denote this one as P. And because we could become confused, I always draw this thing. I say this is the standard basis, this is the B basis, and I know that I'm going to move it this way. So if I have a vector here, which is in the basis B, and here I have a vector here in the standard basis, what should I do? I should write this. The vector in the standard basis is equal to matrix P. So times anyway. So this is another V. Okay, don't worry. This is the same V. Times this is a projection in the basis B. Okay. Now I know that. And by the way, maybe it's better if I denote it like this. So I write this as x, y, and here I have this, right? The capital X, capital Y. This is the notation we are using here. This is an equivalence expression. It's not equal, just showing that where they belong. And then here we are going to get 1 over square root of 2. What was this? 1 minus 1, 1, 1 times. Okay, so this is what we are going to write. And these are equal to xy, right? Because this is how we are denoting those based on that statement. And then let me write here like this. Okay, then let's see what is x and y. The small x, this is equal to 1 over square root of 2, 1 over square root of 2, capital X minus capital Y, and y, the little y, is going to be equal to 1 over square root of 2, capital X plus capital Y. Okay, so this is how both variables are going to change. And then we look at this initial equation here. So now we know how we know x and y, right? This expression is a function of x and y, but little x and y. What happens if we write, instead of little x, we write this expression? So let's transform this representation in the new basis, right? This is something which we like it a lot, okay? So we are specialists in changing the basis from one to another. Let's do it, okay? Let's do what we know best, and let's do what we like the most. So, but let me have a look for the moment. So it looks like, yeah, okay. So this is x and y, and then let's move ahead. We have here 5x squared. So we're going to have here, given these two expressions, we can write here 5. Instead of x squared, if we take this one to the square, this is 5 times 1 over 2, capital X minus capital Y squared, right? Where I wrote here 5x squared plus 5y squared plus 5y squared. Y squared, this is 1 over 2 this is capital X plus capital Y all squared. Now, I might take away this circle discussion. I think we do remember this, what this was. And this is 5 plus minus 6 times x times y. X itself is equal to 1 over square root of 2 times x minus y times y, and y is equal again 1 over square root of 2 x plus y. This is all equal to 2, okay? So now, what we observe is that we can simply, we look at these terms, if we expand all of these, we're going to get, wait a second, so I can write this here on top. We see that this is 5 over 2 times here we have x squared minus 2xy, right? Plus y squared, this is what we get from the first term. The other term is plus x squared plus 2xy plus y squared. So this is what we get from these. And then this whole thing will be multiplied by 5 over 2. So this will be, now I can write the final result right away. You can trust me or you can do it on, later, but let's have a look at this very fast. So this is here. Then we have 1 over square root of 2, 1 over square root of 2 is 1 over 2. This becomes minus 3 times x squared minus y squared. This whole thing is equal to 2. So now we have, this is 5 over 2, that 5 over 2 is still remains. So we can multiply by 2 everywhere. So this becomes minus 6. And this becomes 4, I believe, if I'm not wrong. Then we have here 5x squared, this is 2x squared, right? Times 5, 10. Minus 6, this is 4x squared. So we get here 4x squared. So we took out the x squares, which are here. That's 1. That's 2x squared times 5 is 10. Minus 6 is 4. That's what is left. And then this 2xy cancels out, this minus 2xy cancels out plus 2xy. Then we have y squared. Let me do this to show this different. This minus y squared, we get 2y squared times 5, 10y squared, plus 6y squared, we get plus 16y squared, okay, plus 16y squared. Okay, so we see here that we are done with all the terms on this side. Everything y squared, x squared, and this one we also added it. This is all equal to 4, apparently. So if this is equal to 4, now the first thing that we might notice, that you should notice, is that we do not have coupled terms. We don't have, so if we see here, we have 6yz, we can consider this one. If we see the term xy, then these variables are coupled. Okay, this is how we consider it. And the coupling, it is often observed in the off-diagonal terms. So here, we have this matrix here. Okay, and we see that we have off-diagonal terms.
Yeah.
It's going to couple x and y. Is it clear? You have a question?
No, I was asking. So when we see that in the matrix, they are the diagonal
Terms, yes.
are equal. So it means that it is coupled.
Not that they are equal. Having off-diagonal terms makes them coupled. Okay. Yeah, that's a good question. But now here, what we observe here, we get x. We divide by 4. We get x squared plus 4. Sorry, this is y. This is equal to 1. Now, we started with this polynomial, okay? Now, we ended here with this other polynomial, or this identity or expression. And in fact, if we are to represent this one differently, we can represent it like this. xy, right? These are, let me draw them a little further. They look like a multiplication, but they are not. So this is xy, which is a vector, which is 1 by 2, times another matrix, which is 1, 0, 0, 4. This is 2 by 2. And this, we multiply this one with a capital X, capital Y, which is 2 by 1, and this is equal to 1, right? So, let's see if this is true. If we multiply this like this, we are going to get a vector. So let me multiply this matrix with this. We get here just X, okay? And here I get 4Y. Would you agree? I hope this is not a mistake, because this is X. This is 0 times X plus 4 times Y. This is what we get. If we multiply this with X and Y, this is equal to X times X is X squared. So it looks like I'm correct. Plus 4 Y squared, this is equal to 1. Now, what we can look at now is that we have this matrix representation, which is, wait a second. Oh, I think this is good, yeah. We pick up this one. So let's compare this expression here with this expression here. Now we said that over there, here, this matrix is diagonalized, and the off-diagonal terms are 0. So here we have no coupling. The variables, they are completely independent in the final form where we see them, but there they are, what's the name? They are coupled. So the major thing which is changing here is that we did not, and let's try to look at the problem like this. Let me come to the topic which I like the most, which is the following. So what we did is that we had a standard basis, which x, what was x? Or actually we know the linear transformation, this is it, right? Or maybe the linear transformation, it is better understood from here. So the matrix which enables to pass from one to the other, so we go this way, this is the standard basis. The matrix is 1 over square root of 2, 1 minus 1, 1, 1. But it can also come the other way around, but this is the basis B, and in the real domain, in the xy, this matrix A, this is 5, 5, minus 3, right? And in the new basis, where we reformulated the same equation, but they represented the x and y differently, we get 1, 4, 0, 0. 1, 4, 0, 0. So it looks like from linear transformation, we are seeing how we can represent. So this is a linear transformation, right? This matrix A that we see here, this represents a linear transformation in the standard basis. Okay. Now this other matrix A, this represents a linear transformation but in basis B. And yes, this is how we work. We said this is P, this is P inverse, that's clear. And then here we have the xy. Here we have the capital X, capital Y. Okay, now I can ask you the following question. So how did we transform the original coordinate system? We had the standard basis xy, okay. We had this one here, and we said that we want to rotate the standard basis by pi over 4. So this is what we did, okay? And pi over 4, it is 45 degrees, and we are talking about bringing this basis here, This is not the best way. Sorry, this is here and here. We get some point here. Okay. So now this is our, let's denote this one as X, capital X, and this is okay. So this is capital X and capital Y. Now, how can we draw this equation on the new coordinate system? We can do what we did before when we draw the equation of a circle and of ellipse. So if we set x is equal to 0, what is y? Y is going to be, let's see for a moment, so x equal to 0, then y squared, this will be 1 over 4, so it's going to be half. So if this is 1 and this is 1, we will be here at half. This is also half. Half. This is 1. And okay, this is 1 over 2 minus 1 over 2, 1. So it looks like we can draw this relationship, or not this relationship. Another way to report this one is all the possible numbers, x and y, which satisfy that identity. They compose an ellipse which, in the rotated standard basis, or in the new basis x and y, it's a pure ellipse. And in this new domain, it is much easier for us to distinguish what we are talking about. Okay, so initially, if we have this equation which is written like this, it might be a little difficult to see what the shape is really. But in the new basis, apparently, it's much more obvious what we are talking about. Okay. So another thing that I might add is that what I can suggest for you to find solutions for polynomials that might look like that. You can use graphical techniques. So you can plot the graph of that expression, and you can right away figure out what the solution can be. And there are some softwares which you can download on your cell phone, and one of them that I like the most, I'm writing it here because I find this one very useful, and it might help you a lot. You can download these Desmos. You write these expressions over there, it immediately plots the graph, and it might provide you immediately the solution. Or, of course, you can use these techniques as we showed in here. So, do you have any question for what we did so far? Is it clear?
Professor, I didn't get how we got the A in the P basis.
Okay, the A, right?
Yes, the A matrix.
Okay, why don't you have a look at what's the name? Why don't you have a look at the expression x squared plus 4y squared? But in fact, once you see the matrix A, which is 1, 0, 0, 4, if you, below that expression, I've written how we can obtain those.
Yes, it's x squared y squared times 1 times the matrix gives the expression.
Okay. I'll just try this in a moment, but just give me 1 second. So here, so you're asking how do we get this matrix A, right?
Yes.
But the thing is that only this way you can obtain this identity. So let's multiply. This is A by xy. So here, let's multiply 1, 0 times xy. What is this? 1 times 0. Sorry, 1 times x plus 0 times y, we get x, right? Then 0 times x plus 4 times y is 4y. We get this, right? So multiply these two terms, this right here. Then multiply this one, this transpose with this other vector. We get this. We get x squared plus 4y squared, we get equal to 1. Is it clear now, or?
No, I get how why it's 1, 4, but like if we have an exercise, how are we going to find it?
Ah, you mean given this and you want to figure out this?
Yes.
Oh, this is the best question. This is why that's why we say in this course that the most important topic of linear algebra is diagonalization. We have to figure out a way how to diagonalize this one, okay? And this is the best, a very good question. So it looks like we have to diagonalize that one. How can we do it? We are going to learn in chapter 8, okay? So forget this which was a given here. You are saying that, okay, professor, you have given me a polynomial. Tell me a technique that immediately provides me the solution, and I'm going to say yes. Let's go to chapter 8 and learn this. Okay, and now since you asked this question, I'm sure that you are waiting. We are impatient of starting chapter 8, which is discussing the diagonalization. Okay, so that was a good question, but we're going to see very soon how we get it. Now, so far we are discussing about the linear transformation, the change of basis. I would strongly suggest you to have a look at chapter 7 at the textbook, because we can continue here in the class by covering a few more examples. A few more other exercises, but rather than doing these exercises now, you can cover them in the seminars hours. We can start with chapter 8, which is the diagonalization. And diagonalization, it makes use of eigenvalues and eigenvectors. And the diagonalization at the first stage, we are going to consider only matrices that are square. Okay, so we have square matrices, which can be 3 by 3 or 4 by 4, and we need to find these specific terms that we are hearing here for the first time, which they look like German. Okay, they are German because eigenvectors, I think it's translated like some of you do know. You are very good in English, but you might also know some German. We're going to do this diagonalization. Diagonalization. We're going to do this one by identifying the eigenvalues and the eigenvectors. The German word is here, which means it belongs to the matrix, or is special to the matrix, or unique to the matrix. Which means that every matrix has its own eigenvalue for sure, and it is related. So I can say that this is related to the change of basis. So we know the trick, we know the technique, how we change the basis. This is one example how we do it right here. But now we want to change the basis by changing, or by also the matrix itself. Not only the vectors like here, but also the matrix. Now the way to do this one. So these are the most essential elements, we can say. And another important thing is that we're going to use only a, which is square, n by n. Okay. If it's not n by n, we cannot solve this one. We cannot diagonalize it. It's not that we are so bad. We cannot diagonalize matrix using eigenvalues and eigenvectors if they are non-square. But if a matrix is like 4 by 5, we don't use eigenvectors. We use another technique, which is very modern, very, very powerful, which is the singular value decomposition. So this diagonalization, it can be done either by this construct that we see here, okay, or it can be diagonalized using, let me write this SVD, singular value decomposition, and this is considering cases where m is different from n, which means that the number of rows is different from the number of columns. Now, let's see how we do this. let me write an equation here. We know that A times X. What happens when we multiply a vector by a matrix A? Together in the class, in the previous sessions, we said that always when we multiply a vector with a matrix, what can happen is that we can have rotation, right? And length change. Or the norm of the vector, we have the length change. So the vector, if you remember, we did an example last week. We said we have a vector here which was 0, 1. We multiplied by a matrix which I forget what it was, 0 minus 1, 1 minus 1. We multiplied this vector 0, 1 with this matrix. We got here minus 1, minus 1, which means that we rotated this by an angle of 3 pi over 4. And this is a good example, so you can have a look at the lectures in the last session. And it's a very interesting question. So what happens is that this vector, which is 0, 1, this has a magnitude of 1. Then we get another vector, which has a magnitude of square root of 2. This is how long this is, using the Pythagorean theorem. So in principle, multiplying a matrix A with another vector, we rotate and we change the length. Now, in the eigenvalue problem, or in this new basis, we are going to assume some vectors that we don't rotate them. Okay? Let's take away the rotation. Let's assume that we are working in a basis where, if we multiply them, we just do the length change. What does this mean? This means that if they are not rotated, we write something like this, right? So this is what the eigenvectors do. A matrix rotates all the vectors except its own eigenvectors. So this is the most important equation in linear algebra because it is useful, because it can help us to identify the eigenvalues, which are these values of lambda, okay, that we see here. And we can identify also the eigenvectors, which are these vectors x, okay. So this is our equation, but then you can assume that the size here is n by n, the vector x is n by 1, this lambda is 1 by 1, and this is n by 1. Now, I can ask you the following question. If we are given matrix A, which is n by n, this is a given, okay? Always, when we have an equation, we try to identify what is a given and what we need to find. Here, we need to find here lambda and xn. Xn is unknown, and this is also unknown. This is to find. How many unknowns do we have? If you're looking for xn, Sapayora ka. If the matrix is 4 by 4, okay, we need to find an eigenvector which is 4 by 1. So in this case, we can say that we have 4 unknowns. That's true. We have 4 unknowns. So here we have also n unknowns. N unknowns. Yeah, no unknowns. But the point is that we have n unknowns only if we have, let's say, a single eigenvector. But what if we have few eigenvectors or many eigenvectors? Then that means that we have more unknowns. Now the question is, let's try to identify how we can find an x. In order to solve this equation, what we can do is the following. We can have here a x, where a is n by n, x is n by 1, minus lambda. This is equal to what? 0. So we get this. So this is lambda x. Lambda x, yes. So this is n by 1. Now the question is, how can we deal with this? What we can do here is that we can multiply here. Say it again.
Я поставил factorization x.
Yes, we can factor out the x, and we get the following. We get a minus lambda I, okay, times x. This is equal to 0. Now, this matrix here, this notation, we can write this one as b times the vector x. This is equal to 0. Okay? What is this? finding the solution for this, what does this correspond to?
Unique solution.
Null space.
Yes, that's true. So finding the solution for x is the same way as trying to identify the null space of B or the null space of A minus lambda I. So often, if you are in an exam, in a midterm or in a homework, whenever you are asked to find the eigenvalues and eigenvectors, the first thing you should do, sometimes it's very, it looks bad to my eyes, that leaving this one empty. Whenever you have a problem to find eigenvalues and eigenvectors, immediately you identify this, it's not difficult, and then you try to solve for the null space. Now, the thing is that here, what is the first solution? What could be one possible solution?
The trivial solution?
That's correct. So one of the solutions would be the trivial one. This would be a trivial solution, okay, but we don't want only the trivial solutions, because a trivial solution, we're looking for a vector, and a trivial solution, it will be just a point, the origin of the coordinate system. So we need a solution, so let's say it like this. This system has solution including x different from 0 only if the determinant of B is equal to 0. Okay? So what we need to do is that we should immediately try to, let me think, we should immediately write down the determinant of this new made-up matrix, and when we write the determinant, we are going to have a polynomial. And this polynomial, this is called characteristic. Characteristic polynomial. And so, wait a second, so I believe, let's keep it here for a moment. Now, let's try to identify what could be the values or eigenvectors of specific cases. Wait a second. Or why don't we have a look at this matrix which we have provided here? Or let's give something like, well, let's get this A. This is equal to 7, 2, minus 15, minus 4. Question is the same. Question is this. And then what we need to do is immediately we write the following. A minus lambda I will be equal to 7 minus 15, 2 minus 4 minus lambda 0, 0, lambda. Okay, and this is going to be equal to, I believe you can see this part is, so this is equal to 7 minus lambda minus 15 and 2 minus 4 minus lambda. Okay, and then, so this is the B matrix that we see here, and we want to get values solutions x, but that are different from 0 only when the determinant of B is equal to 0. So let's write down what is the determinant of this matrix here. Determinant of that matrix is equal to 7 minus lambda times minus 4 minus lambda plus 30. This should be equal to 0. Now, okay, we're going over this, but we can always, so we learn the technique, right? But let's go back to what this really means. So we want to have here a non-zero solution x. What does it mean to have a solution x which is different from 0? This means that there is a linear combination of the columns of B, and they are linearly dependent. Okay, so I want this to be clear to you that when x is different from 0, that means that the columns of B are linearly dependent. If they are linearly dependent, that means that if we combine them, we are going to get a row or a column which is full of zeros. We know that if in a matrix one row or a full column is all zeros, then the determinant should be equal to 0, right? So let's not take things for granted. We already know this. We already know that the determinant of B will be 0 because a linear combination of those, which includes x different from 0, means that will be 0. So now let's continue. Let's solve this problem. The first approach is that we need to find lambda. So this is what we need to figure out first. What is lambda? Let's multiply. Here we have minus 28. Minus 7 lambda plus 4 lambda plus lambda squared plus 30. This is 0. We have here lambda squared minus 3 lambda. Then we have plus 2. This is equal to 0. Now, this expression, this can be, these lambdas, we can factor them out as lambda lambda. And this 2, it can be expressed as minus 2 minus 1, right? So if we multiply minus 2 with minus 1, we get this 2. So then it looks like we can simply write down that this is lambda minus 2 times lambda minus 1, and this will be equal to 0. So this is a polynomial of the second order. So this is, let's have a look. This is P2 in x. This is polynomial of the second order in x. So from here, we expect two solutions, okay? We need two solutions.
1 and 2.
Yeah, there are 1 and 2. So here we have lambda 1 is equal to 2. Lambda 2 is equal to 1. Now, lambda 1 is equal to 2. This becomes like a mess. Allow me to write lambda 1 is equal to 1. Okay, otherwise it will be like a game when we use them. So lambda 1 is equal to 1, lambda 2 is equal to 2. This looks simpler. And then we need to identify, so let's see. So we did the first part. We found lambda, okay? We have 2 eigenvalues. That's good. 2 eigenvalues that we can substitute in this initial equation, okay? Now, what is the unknown? The unknown for us is x. The matrix is 2 by 2. What is the dimension of the vector x? It's going to be 2 by 1. We have 2 unknown values, which are a and b. So then, let's write here, what we get here is that what was a? It is 7 minus 15 to minus 4 times the unknown values a and b. This will be equal to the ab. Okay? Because a times lambda is equal to 1, sorry, a times x is equal to 1 times x. What did we say? We said that a matrix does not rotate its eigenvectors. So this is equal to 1, and then from the first equation we get 7a minus 15b is equal to what? What is this? This is equal to a, right? What is the second equation? Who can read the second equation for me?
2 times a
Yes.
minus 4b
Yes, is
equal to b.
Okay, now let me ask you this. How many unknowns do we have?
2.
How many equations do we need?
2. 4.
But do we have two equations on the board? Do we have 2 equations on the board?
Yes.
I can say no, okay? So the second one, we take it away. Technically, we should not have two equations on the board. Why? Because the determinant of this matrix is equal to 0. And now I'm assuming I have only the first one. And let's check whether I'm right or not. So I need a foot of space here. So this is 7a minus a. So from the first equation, what do we get here? Do you see that this is 6a is equal to 15b? Right. And the second equation, what this tells, it tells that 2a This is equal to, what is this? 5b. Are they very much different? It's the same equation, right? So that's why we can consider that this one is not existent, because if we divide the first expression by 3, we get 2a is equal to 5b. And the second equation is still 2a is equal to 5b. So I want you to be careful, and you should expect that the second equation, it is linearly dependent to the first one, because the determinant is 0. Why is this? Because if you look at this carefully, if you take this -1 to this other side, so let's assume that you put, what is this number? This 1, right? So then this matrix will be 7 minus 1 is 6, minus 15, 2, minus 4, minus 1, minus 5. So you can see this one, that this is, the determinant of this one is equal to 0, because the first row is the second row times 3. Fine. This is what we're going to get. When we find eigenvalues and eigenvectors, we find a direction. We cannot find a single point, which means the following. Let's try to solve this one. We have 6a is equal to 15b. Let's divide by 3, and we get 2a is equal to 3b. Then we say that ab, this vector, is equal to what? Give me a pair of numbers which satisfy this condition. Can you give me a pair of numbers AB which satisfy this equation?
3 and 2.
That's correct. 3 and 2, that's one solution. Another solution is 6 and 4. Another solution is -3, -2. Would you agree? And many more. So this is the first eigenvector. Another thing is that we want the eigenvectors to have magnitude 1, to be unity vector. So what we can do is that we can normalize. If you notice here, we are putting comma. So this is eigenvector, this is eigenvector, this is eigenvector. We can also denote what is the magnitude of this vector 3, 2. 9 plus 4, 1 over square root of 13 times 3, 2. This is also an eigenvector, but we like this eigenvector a lot because it has unit length. Now, let's find the other eigenvector, which is the least useful part on the board. Well, let's take away this one. And here, we write down that we have 7 minus 15 to minus 4 times AB. This is equal to 2AB. Right? We install here the second value for lambda, and the first equation, it is 7a minus 15b. This is equal to 2a. The second equation, you don't need to write. I don't need to write. Okay, so this is because the second one, for sure, it is going to be linearly dependent to the first one. Let's not waste time. And from this relationship here, we get 7a minus 2a. This is equal to, what is this? 5a. This is equal to 15b. So we get that a is equal to 3b, which means that the eigenvector here, it looks like ab is equal to a pair of numbers which satisfy this condition is what? 3, 1 is a choice, right? Similarly, -3, -1, it also satisfies the same condition. And another one, we can also define a vector which has unit length 1, which is 1 over square root of 10, 3, 1. Okay, so it looks like we found eigenvalues, we found also the eigenvectors, and this is. Now, what I want you to look as an exercise is the following. So this was the example we covered. The solutions are shown here. These are the eigenvalues, and these are the eigenvectors here and here. Now, as an exercise, I want you to find the eigenvalues and eigenvectors of this matrix. The matrix that we solved in the previous example, just have a look of what are the eigenvalues and the eigenvectors. Do you have any questions?
Professor, I had only one question. How did we find L1 equals to 1 and L2 equals to 2?
Those were the solution of the second order polynomial in lambda.
Okay.
Okay, so we have here, I can write this again, but I can use some space over there. So look at this matrix. How did we find eigenvalues? This is a good question, please don't forget it. But whenever we are trying to find eigenvalues, the first thing that we write is this A minus lambda I, which is here, okay, which is also like this. Please never forget that we are subtracting these lambdas only along the diagonal. And then we write down the determinant, which should be equal to 0. What is the determinant of this matrix? A 2 by 2 matrix is this number times this number minus the product between these two numbers. Okay? So we get here 7 minus lambda. We get 7 minus lambda times minus 4 minus lambda, minus 4 minus lambda, plus 30 is equal to 0. Plus 30 is equal to 0. So if we solve this one, we get these two solutions. If we multiply what we got before, we got lambda squared minus 3 lambda plus 2, this was equal to 0. This is the polynomial of the second order, which has solutions that look like this, okay? Pastaj mund ta zgjidhësh edhe me dallorin e mban mend?
Po.
Okay. Pra, me dallor edhe është e lehtë. So if you use the discriminant, you can use it like this. We know that lambda 1, lambda 2 is equal to minus b plus minus b squared minus 4ac divided by 2a, and then you know what we should do. Minus b is equal to 3 plus minus the square root of b squared, it's 9, minus 4ac, or the minus 8, divided by 2a divided by 2. So here we get 3 plus minus 1 divided by 2. So this is 3 plus 1 divided by 2, and 3 minus 1 divided by 2. Is it clear?
Yes, thank you.
Okay. You are welcome. Any other question? So if you have no more questions, we can stop this. But I just want to okay, let's close this one first.